How's it going? Have a good weekend? Okay, where's that? Missed you guys Friday. I appreciate your posting, your posts. Each one of you have been all right. Very nice. Appreciate my
each upload, yeah. Everyone starts with a new dynamic pose. This.
Oh, like in the like what the video.
Yeah, very easy to distinguish.
Yeah, YouTube just fixed that. It's
Really?
They just pick a random frame. Right? I can upload so I can make like better videos, and I can mix them, and I can go take my video editing software, have title and stuff. So I just uploaded it, and YouTube gets a first frame. So there you go. It's the lazy version. All right, so I know we're missing Zach. Probably still. Looks like what else? Oh, Andrew usually sits here, right? Everyone's got their assigned spots now. We've all worked that out. We don't want to mix it up. We want to sit in these spots when someone else might come. Okay. I guess it helps that like you can't sit in the other seats, right? Andrew, we were just talking. Your spot was open.
I'm sorry.
We just figured,
The
everyone
world.
has their assigned seats now, so it's clear who wasn't here. So, Although Mark, you were over here before, weren't you? Oh, you like to mix it up. You don't want to keep it the same. Okay. Anyway, so all right. Well, not to put you on the spot. So maybe we could just start with opening prayer, and then we'll into more vectors today. Do I have anybody who's interested in giving that? You make me do it? All right, go ahead.
Dear Holy Father, we're thankful for the opportunity that we have this morning to be your transport. And please help us that we may be able to understand the material. And please help Dr. Tree that he may be able to know how to best explain the material to us. We say these things in the name of Jesus Christ.
Amen. All right. Okay, we got Zoom going. We got Zach on there. Hey there, Zach. What's up, Andrew?
I was just gonna ask you, did you do the homework that was due today?
Did I do the homework that was due to
Because I know you said you usually do.
I did do the homework.
Is this typical of an assignment? Is it less work? Is it
That one was longer than the
pretty?
first two.
This is pretty beast.
Yeah, that seems like, I think that's more and more that's going to be like. Yeah, the first couple were, anyway, I mean, it kind of depends on the pace we get in here, right? Because there's kind of like two problems a lecture from the things. And then if I go slow, you guys got to be like, slow down. Because anyway, because like we planned on 2 lectures for vectors and tensors, but we only got to here, right? We'll probably have to do 3. So the special problem 1 and 2 go with the appendix, basically. Anyway, so, but yeah, like some of that was, I think, that there was some of the stuff from chapter 2 that was kind of in the lectures from the previous weeks. And so then that had got pushed back. So there's maybe 1 extra problem sort of in there because of that. But yeah, that's kind of so that probably took us what? It took me maybe 6 or 7 hours to do that homework. So it probably took you guys maybe 9 or 10, I'd guess, maybe to do that homework. Is that about right? So I don't know. I'm seeing some nods up and down. I don't know. Maybe you didn't track. But that's about right for a graduate class, about 3 hours outside of class for every class for a homework problem. So my advice would be to do the problems, like for the lecturers, not wait, right? Not wait till the end. So like right now I know I have to go put up the other problem for next week, but there's special problems 1 and 2, which are up there, are just some of the problems to work through from the appendix that work through some of the vector and tensor algebra stuff that we're doing for some practice. So I wouldn't wait to do that until, Saturday, or you'll have a bummer Saturday. Yeah. Okay. All right. That was a stressful weekend then. Okay. Sorry about that.
It was a homework.
Andrew's like, for me, 6 hours took you to do that? It took me a couple minutes. I don't know what your problem is.
No more like were you doing
The one that was hard, the thing that took me a really long time this last week of class was not actually the homework, it was the problem that I kind of skipped in the lecture. The other fluid flow problem. Like the day we did momentum energy balances, or the cylinder problem, falling cylinder. And Dr. Pitt's notes, he had spent an entire day doing that problem. And it took me 10 pages and I was like, I'm gonna highlight this problem. But I got grumpy with it, so I had to like finish it. And that took me like 4 or 5 hours to finish that out. So that was kind of grumpy. But anyway, I don't think I'm gonna do that problem next year. Yeah, so, all right, so let's get into it today so we can make some progress on vectors. So if you remember, just to kind of remind us, so all of this stuff you should have from the last lecture, at least outlined, okay, and then this is the outline for, in principle, today's lecture. But we talked about what vectors and tensors are. We talked about the idea of a vector space and then an object in a vector space. And we talked about a basis set, right, and basis vectors and how we need to represent them. And then we talked about scalars of vectors and tensors, sort of the 0D, 1D, 2D version of directions, and a little bit about notation. Gibbs notation, index notation, and some matrix notation. And then we started talking about algebra, and we really, really quickly went through the properties, right? We talked about commutative properties and those kind of things you'd expect. Those are actually, for a vector space, a lot of those properties are identities, so you need to have that to exist to be in a vector space, but that's kind of just like aside. And then we started going through products. We talked about the outer product, the dyad or tensor product, which is how you go from 2 vectors to a tensor. So like if you put VV, right, which we see in a convective flux, right, or sometimes we'll see grad V, that's a dyadic product. We have dot product to the inner product, which is the same as matrix multiplication, which we saw. A double dot product, which was tensor and then the transpose of a tensor, and then you do element-wise multiplication and sum them all up. That was a scalar product of 2 tensors. And we got to that point, and we didn't get to the cross product yet. So we'll talk about that real quick. And then we'll talk about a couple other properties real quick, and then some vector and tensor calculus. And then we're going to start talking about coordinate systems. And if I had to guess, I guess we'll get to here by the end of the lecture today, coordinate systems. And then we'll see, maybe we'll get into the algebra and calculus and curvilinear coordinates. And that is the subject of special problem 2. So special problem 1 is this stuff and this stuff. And so I sent you that email over the weekend and said, don't do special problem 1 yet if you haven't already done it. But I mean, you're welcome to. If you're having fun, you need to stop the fun. But anyway, so that's a quick review where we are. Any questions about that to this point? So I don't know if everything I taught was that clear the first time through. So this would be a good spot to maybe pause and you tried to work through something, anything that you're stuck on. All right, here's mine. Okay, so let's talk about the line here. Let's get to 2B, and we're gonna. So this is vector and tensor algebra. Okay, and we're going to jump right into the cross product. Okay, so well, I picked up. I saw crosses, but that's because we're doing curls. Okay. So a cross product, we were kind of classifying these different kind of products by what went in and what came out, right? So for example, I said in the double dot product, we had a tensor and a tensor, and then you get a scalar out. So it's sort of 2, 2, and then -4 for the double dot product. So in the case of a cross product, we have a vector, and out comes another vector. Okay. The cross product is kind of weird. Can't really don't really have a cross product that's the same in 2 dimensions. It's really only in 3 dimensions that we have a cross product. It has to do with linear algebra that frankly I didn't fully understand, but it's the cross product sort of defines a tensor, and then it works out that in 3 dimensions that ends up giving a vector. Sort of like a 2 minus the number of dimensions, or 3 minus, or let's see, the number of dimensions minus 2 is what you end up with. So in three dimensions, that's 3 minus 1. But you end up with weird things with cross products in another dimension. And physically, we really don't care about them, so I'm just going to kind of pass that. If you want, I'll forward you the like 2 or 3 articles I've written about it, mostly on Wikipedia and various math sources. You probably don't want, but I'm happy to sort of forward that stuff. So the idea on the cross product here, right, if you remember, I have 2 vectors, v cross w. The definition looks like this. I'm going to do this triple sum over I, j, k. And there's this little guy we'll talk about here, permutation tensor. And then we have our unit vector I, and then vj, w, k. Okay? And this guy, epsilon ijk, oops, jk, is defined, it's kind of like our Kronecker delta. If you remember, that had a 1 and a 0. This is defining a 1 and a minus 1 and a 0. And the 1 is when I get 1, 2, 3, let's see, 1, 2, 3, 3, 1, 2, and one more, which would be 2, 3, 1. Yep. And then this one is 3, 2, 1, 1, 3, 2, and 2, 1, 3. And this one is all of it. Okay, when I get repeated this usually. Okay, so a couple things about this. First, the way that I see to remember which these are is that I start with 1, 2, 3, and then I rotate it around the loop. So I just move 3 to the beginning, and then I move it around the loop. 2 comes to the beginning. Okay. Whereas this one, it's backwards, 3, 2, 1, 3 goes over, the 1 comes to the front, right? Okay, so you can kind of see how that goes around, okay? And this defines essentially a determinant, all right? So you can write all these sums out, and what you'll get is the following: v cross w of delta 1, 2, 3, v1, v2, 3, other 1, 2, 3, where these are the components of the vector, okay? And then if you go to write this out, right, you remember how to do determinants, I hope. You do this one times this one minus that one times that one, all multiplied by that guy, right? So I have v2 w3 minus w2 v3 delta 1, right? And if you look, so a good exercise to do outside of class is to write these i's, j's, and k's as sums over 1, 2, 3, okay? And plug these in, and then when I finish writing this formula out, verify that these are all the same thing. This means all the same thing, okay? So this one, then let's see, I have subtract. Now I cover that one up, right? And I do that times that minus that times that. You guys remember this from determinants? v1, w3 minus v3, w1, delta 2, plus, last one, cover that guy up, I do v1, w2 minus w1, v2, delta 3. Okay? And if you remember physically, what this means is that I've got these 2 vectors like this. Let's see what I can show you. v1 and w, not v1, v, w. Okay, and I get the new v cross w, which is perpendicular to those guys, right? So there's right angles of both of those. Okay, and the direction is governed by the right-hand rule and right-handed coordinate system. So v cross w will go. All right, hopefully that's coming back. So that's a cross product. Questions about the cross product?
I have a question.
Yeah, far away.
So delta 1, delta 2, and delta 3, normally delta we use for the identity matrix. What makes the 1, 2, and 3 different? Is it like the first column, second column, third column?
Yeah, so these here would be like delta 1 would be like delta x. Y, and Z. So if you remember, so what Bert is kind of confusing on the notation. So let's review what he uses delta for, okay? So he uses delta for unit vectors. That are basis vectors. Right? So that would be like in my coordinate system. If I had a Cartesian coordinate system, x, y, z, delta x is going to be that unit vector for x, right? And then delta y and delta z, or excuse me, not delta y. Okay, so that's what we're talking about here. So I wrote 1, 2, 3 instead of x, y, z, sort of be a little more generic. We'll see that for different coordinate systems, it won't matter. The product will be the same. Yeah.
So does that mean the first term in the V cross product W is just the x component of the resulting vector?
This one, and this term will be x
Yeah,
component.
that's-
Exactly. That's exactly right. Great one. Okay. But Bert also uses delta with 2 underlines on my board, and that's the identity matrix. Okay. There's another delta that he uses. Okay. Finally, he uses delta ij to be the Kronecker delta 1, 0. So that would be 1 if I equals j, 0 if I does not equal j. Okay. So now there's really only a subtle difference between these two guys, right? Because this kind of means that, right? If you look at it, okay. Except this is a tensor because it has a basis, right? We're expressing in some coordinate system, as opposed to this guy, which is just some set of indices. Okay, that's a really subtle difference. You can think of them both kind of as a matrix if you want, but we're going to talk a little bit like about coordinate systems and basis sets. So it's kind of we're graduate students now. We can have that kind of subtle difference, right? We can understand that abstractions. Okay, that makes sense, Zach.
Yeah, thank you so much.
All right, that was a great question. Yeah, hopefully that clarifies it. Okay, so we did cross product, we did dot product. So the last thing is just to define a couple. Here's the thing I wrote in my properties. That kind of goes along with that. You can write the unit tensor here, right? This delta 2 underlines is going to be delta ij unit vector I, unit vector j, which is dyadic product, right? So that's what I mean by, if we want the tensor version of this, right? But that expresses all of our deltas in one confusing spot, right? We've got the delta identity matrix, we've got the Kronecker delta, and then we have the unit vectors I and j. Okay, which could be x, y, or x, z. Okay. All right. You seem like kind of hard to tell sometimes with the mask. You see kind of confusing stairs. So if that's confusing, please ask. All right. Couple other things just to say about other properties. I guess that's these are like other things I just wanted to point out to you. So one was this idea about the transpose. Okay, so if I wanted to write A transpose, so they use a little, is it a dagger or a plus in the book? I can't remember. Kind of weird that they don't use a T. But you can write this as, in our index notation, Eij transpose, and what that'll do is just flip the order of the indices when we write index notation. Okay, so now the first one, remember, it always goes row, column. Now the rows are j and the columns are I. Okay, so that's flipped that right. Okay, a couple other things. Remember matrices, or if you haven't seen it before, the trace of a matrix. You guys know what a trace is? Is that a new thing? Okay, the trace is the sum over the diagonal elements. So the sum over I of AII. So for instance, the trace of the identity matrix would be the sum of the diagonals, which is what? Question checking for understanding. You think, Christina, what's the trace of the identity matrix? 3, right? So you'll see this a lot when people have a 1/3 good trace of something, okay? Because that'll be 1, right? So that's something to do that. We saw that actually in the Newton's law of viscosity, right? Where we subtracted that. We had this like third that was hanging around when we had that dilatational viscosity. Remember that? That became because we were subtracting out the trace because we wanted to get rid of the trace in that tensor. You can go back and look at your notes on that. Another quick thing, a lot of space here, so all that over here. Do some erasing. Real quick, just to put these up. We've got, how do I get components? I have, if I wanted, just say the x component of the velocity vector, I can take a dot with the x unit vector, right? So that's just going to give me out, write that out, right? That's going to be the sum over vi delta I dotted with delta x, right? And if I have an orthonormal coordinate system, which we'll talk about in just a second, right? This is going to give me the vi, this is going to be delta I x. That's my Kronecker delta. So the only time that this is not 0 is when I'm at x. And so this is just going to give me vx, right? Another way to think about that is if I have some vector, right, and I take the, you know, and this is the x direction, the y direction. I take the dot product, I'm going to get the projection in the x direction, right? Yes. So, yeah. So that's the way we get it for a vector. For a tensor, I have a tensor T. I'm going to do a dot product on both sides. So now let me call this one, just for an example, I'll do delta x on that side and delta y on that side. Okay, so now I can write that as the sum over I, the sum over j. I've got, I'll put delta I, delta j, unit vectors, Tij. That's my tensor. And then I'm doing a dot product on the left. Oops, I forgot the dot there. And a dot product on the right. And remember, with tensors, I can't commute. So I can't just move my dot product wherever I want. So I'm going to have over here delta x dotted, and over here I'm going to have delta y dotted. Okay, so now that one I can rewrite. I'm doing some of these proofs just here real quick to give you a flavor for them. So I have I, sum over j, delta x dot delta I. That's going to give me a delta ix for my Kronecker delta. There's a delta xi technically, but it's symmetric. So same thing. And then this dot product here, I can pull out the Tij from that dot. I can just pull it out there wherever I want. So I can write now a delta Kronecker delta jy, and then I have Tij. That makes sense. And then remember that these deltas, right? One way to think about them in index notation is that since they're only ones when I have x equals I can just replace the index I want over here with either I or x. Well, in this case, I'm doing the x1, so that makes more sense, right? So the only time this is going to be 1 is when I is equal to x, so all the other sums go away. Same thing on the j, and I end up with t xy. So notice that the component I got respects the order of the dot products I did. I did the left dot product, that gives me the x there. If I do the y dot product, it gives me the y there. Okay, so just picking out the component by doing that, sort of undoing the dyad product, if you want to think of it that way. Yeah, I picked out one on one side and on the other side. Right? Forgot to say something over here that I wanted to point out. A matrix that where the transpose is equal to the matrix, that's symmetric, right? We also have an anti-symmetric matrix. There's a minus. So I have, you know, Aij is equal to minus AjI. That's symmetric. Right? Just wanted to. All right, well, I'm going to erase for a second, but I'll stop for questions on it. There's like lots of minutia in transport, isn't there, with this kind of stuff, right? This is kind of like we have to get good at doing this kind of stuff. And you can see in a problem, like we did these shell balances, right? And there's sort of that setting up step and the understanding step. And then there's the math step where you got to do all this algebra and this, right? And you have to practice enough at this that you're not scared or intimidated by that part, so that you can step back and think about the physical intuition and the results and what they mean. Like one of the hopes, and I think this is the point of a lot of these kind of stuff in graduate school, is that we want you to be able to go to the literature and pick up a paper that has transport in it and see the math and have an understanding enough that it's helpful to like make something precise, as opposed to something that just confuses you and makes you feel frustrated, right? So like, it's kind of painful to go through this part, right? Like, no one really enjoys coordinate systems. Like that's, I mean, like, there's probably a mathematician somewhere that enjoys it. But most of the engineers I know, right, we don't like really enjoy that. That's not why we're in this. But we kind of have to like build our skills. Anyway, so if this gets boring for you, sorry, it's not my favorite subject either. But like we have to, it's kind of like being able to dribble a basketball. It's all more fun to play basketball if you can dribble, right? If you can't dribble, it doesn't matter how fast you can run, right? So we need to have that skill so we can sort of forget about it and move on, right? And so if you're good at this, hone it a little better. You can always do more drills. If you're not good at this, now's the time to really like dig in and kind of get over that hump, right? So that this doesn't intimidate you. Okay? All right. So here's my maybe not that exciting pep talk. My marker's starting to run out. Speaking of basketball, see if I can make it in. All right, duck down. Oh, I hit this. Nice for you. Okay. The pass. It was an assist, really. Okay. He's dunked it. So I'll take the assist. It's like my 3-pointer this one. All right. All right. So the important part of, and we're going to focus on Cartesian coordinates here for a minute. Get to others. Maybe we won't even get to them. Okay. Almost everything is starts out with our gradient operator, and the gradient operator is defined as the sum over all the unit vectors multiplied by their respective derivative. Okay, so you know the x derivative in x direction, the y derivative in the y direction. Right, we've seen this before. Okay, so we can take the operation on a scalar, grad s. So the gradient operator is sometimes called nabla, del. I remember upside down triangle sometimes. Okay, if I'm joking around, right? Grad s. So we just plug in an s here. Delta I ds dxi. Okay. In index notation, maybe I'll put index notation. We'll simplify this whole thing to like a partial I. Okay, it's like the really fast way of writing it. So here, for instance, we might write partial I s. We can also apply this to a vector. You can have grad v. So notice that that's I add a product between gradient, and the vector. So that's going to give us a tensor. So now we're going to need the sum over I, sum over j, delta I, d, v, j, dx, I. I need to put a delta j in there. Delta I. Okay. It's important that we get the indices right on the j and the I here, right? So this one is I, that one's j. So the index notation for this di vj, I think is really useful, help remember. Okay, one thing that's really easy to do is to put the I on the top and the j on the bottom. It's kind of natural for whatever reason. But you have to remember that the gradient is the first part. So the derivative I has to go on the bottom. So this goes from, right, a vector here. We did this operation, we get a tensor. So that's the gradient operation. Right. So to do that, you just take the derivatives. If you had some velocity vector, right, you have to take the derivatives of all of those guys. So now let's see. We've got a divergence operator. And a divergence is the gradient with a dot product, right? So you can kind of think this one here was just on a scalar, or this was like a dyad, right? We're going up by 1. Here, we're going to come back down. So I can't do a divergence on a scalar. That doesn't make any sense, right? I need to have a vector. So if I have a vector, I have del dot v, for example. So let me write up what the divergence is up here too. So the divergence, I have a sum over I delta I d dxi, and then I have the delta ij, product of delta, which comes from dot product, right? So anytime I see a dot product, I can just write the product of delta in there. So if I write this guy out, I'm just going to skip the index notation because it makes my life easier. Ij, right? So I can just take the delta ij out, put it right there. Okay. I have the derivative here, I have vj, okay? And so I get di vi. So now I have the repeated index, which you remember back in our other notation means we're going to have a sum over the delta I. When I have the repeated index, that means sum. So I guess I'm kind of slipping into index notation here as I start to work through some of these proofs with the calculus or some of these just expositions. So for me, when I do this, you can write out all of these sums and these things. And what happens with index notation is it's really just a sloppy version of the sums that has kind of some rules so that we don't screw it up, right? And so that's what I've done here. I could copy this sum down, okay, or I and j, and I could have the dot product, you know, and give me the delta ij, and then I could, anyway, but this is just so much faster to do, right, and to see what's going to happen there in that divergence, right? I'm going to take the sum, right? You've probably seen that before. So that'll be like dvx dx plus dvy y plus dvc. And you see how that is the same thing as that? You see how that's the same? Okay. So, and this is a lot easier to write than that, right? And it's a lot easier to write than that, right? Okay. All right. So that's kind of the benefit of index notation. All right. Let's see the curl. We can do a similar thing. So I have del cross. It's going to be the sum over d dx j. Okay, so the curl is the cross product of the gradient operator with a vector. So another way, let's see, if I have v, I get now the sum over j k, and let's have the same thing here. Delta I, handwriting gets worse as I get forward, I apologize. Epsilon I j k d v k v x j. Right, and we're going to write this, we can write the same determinant that we just did for the curl previously, but now we've got, so I'm going to put this up here. Now delta 1, delta 2, delta 3, and d dx1, d dx2, d dx3, d1, d2, dx dy of z. Okay, I'm not going to write that out, but you can determine it right. Right. Say that again, Zach.
Can I ask you a quick question?
Yeah.
When you wrote the curl as del cross x, well, you only had 2 sigmas, but then when we added a v, we now have 3 summation terms, and I was just wondering where that 3rd term comes in.
Yeah, that's just because if you remember velocity or any vector, I can write as the sum over the components with the unit vectors. So in this case, because I is the one, I'm using the k. Okay, and yeah, so that's where. Does that answer that question? I see your hand.
Yeah, thank you.
Yes.
Remind me, does the vertical lines, does that mean take the determinant?
Yeah, the determinants. That's right. That's right. Notice that I forgot to write the tensor. I better do that one real quick. So right here, I forgot. You have space in your notes, you can do it here. I don't have space on the board. But we forgot the tensor divergence. Okay. So I'm gonna come here over here. Okay. So I've got the. It's very similar to this, right? So if I do the index notation for this one, we have delta I, and then tau jk, and then, or excuse me, I have di, and then I have a delta for my Kronecker delta, which is ij, right? Because that's the dot product in between those 2 indices, right? So then that delta ij makes one of these go away. I can pick which one. So I'll just keep I. So I have delta I, tau I, k. Okay. So what's going on here is I have the summation over the i's. That k is a free index. So this goes from, vector dotted with a tensor and a vector. So I can probably write that out just to help us see. That's going to be d x1. I'm going to see that as x. I don't want to keep switching on my notes. I have to fix that next year. T x k plus d or d dy dyk plus d dz. I'm saying t is the tau zk. Okay, you see how that works? So then that ends up as a vector, okay, because I have that k index that's free. So that depends on what tau is, right? So that's going to be row column. So it's going to be some column of tau. rows. Okay, all right. We're going extra slow today. I don't know if this is good or boring. Hopefully it's on. Good. Andrew says it is good. Okay. Okay. Oh, did you get another one? So does the blue one have a hard time showing up on the screen? You just like it better?
They just have black.
Thank you. Thanks for getting it. Appreciate it. I'm just curious because if the blue one doesn't show up, then I just won't use it, right? It's okay. Zach, can you see the blue one just out of curiosity?
Yep. Yes, I can.
Yeah. Okay. All right. Good. I just want to make sure. I'm happy to use the black one too. All right. The last one I'm going to put up here is the Laplacian. This marker's nice. Like butter. Okay. That's kind of stupid, but anyway. All right. So this is a scalar operator. Okay. So the Laplacian is a del dot with a del. So we write that out in next notation or in the definition. We've got sum over I, sum over j, delta ij, d dxi, d dxj. Okay. So where I've had a delta, this guy came from, I had a delta, I guess I'd call it delta I and a delta j that I thought was got, right? So that's where that delta ij came from. So if you notice, this is delta ij, right? So that means my I and j are going to be the same. So this means I just end up with the sum over I of a second derivative of dxi squared. Okay. In index notation, we'll simplify this all the way to di squared, or sometimes di if we want. Either way. Okay. So you can do the Laplacian on a scalar, right? You can do the Laplacian on a vector, okay? And the Laplacian on a tensor, because it's a scalar operator. So that's going to end up just as a scalar also. Okay, and in Cartesian coordinates, it's just this, right? So this will just be ds dx squared set. Okay, and if I take the vector, it's really boring. I just put the vector in there. Okay, if it's a tensor, I just put the tensor in there. Just replace s with. So let's see. I think that was all I want to say about calculus. So I want to summarize notation real quick. We don't know start talking about coordinate system. Summary of notation. All right, so I'm just going to put these up here. Remind us about index versus index notation. Help you do a couple of this. So I've got v for a vector. This one, subscript I. I have u dot v. Here this gets ui vi. Okay? And in both of these cases, there are index notation rules. Okay, so if I have a free index here, okay, I have a vector direction. Okay, so I've been saying that, but I'm trying to sort of summarize up here and make sure we're all on the same page here. Okay, so vector dimension is another way Okay, and this one here, I have repeated index. Okay, and that means I have an implied summation. So anywhere where I have those two indices together, what I've really done right was a dot product that sums over them all. Okay, so that's added. Right, so some of the other things we had were delta or nabla or whatever. This gives us DI. Delta, sorry, delta. Come on, right? Del dot V gives us DI VI. We have grad squared, which we just did, which we get DI squared. We have U cross V. This one we're going to get EIJK, epsilon IJK, UJ VK. Fix that V. Looks like an N. Okay, so just looking at this one, where are the sums and which is the free index? Who can tell me on that one?
Sums are IJ, free is K.
Close. Okay, the sums are on K and J. You see that? And then the free index is the I. Okay, so if we were to write that out, the direction will have the I, the direction from the I, right? So we write that out with all the sums. Okay, so you see, you start to stare at these a while. You start to just see where they pair and just see the sum in those, okay? And then see that the vector is the I there. Okay, we can write the same thing with the grad cross V. Now we get epsilon IJK, okay? And then we have the delta J VK. Okay. So let me show you just an example proof. The kind of stuff I think is on the homework special problem 2. Maybe it's not. I can't remember which one. I have del dot SV. Okay, so I want to do essentially the product rule, but with the divergence. I want to look at that. You can look it up in your book. The answer is del S dot V. That's together. Plus S divergence of this, or whatever it is. Okay, so looks like a product rule, but you kind of have to figure out where does the dot go? How do I do this? Okay, in index notation, is really simple to do. Okay, so if I write this like that, I see del dot SV. I can immediately write down DI of SVI. Right? See, that's my repeated index. Okay, everything's good there. Now all I have to do is the product rule I learned in calculus and pull out the S and the curve. So now I write S DI VI plus, and then I pull out the VI instead. I do VI DI S. Okay, that's just the same thing I learned in freshman calculus. Okay, so now I can rewrite that back in this notation. Okay, you can see they're switched around, but this is V dot del S. Okay, so V dot S, and this one is S del dot V. Okay, same thing, right? Remember that the dot product here for vectors commutes. So that's okay. Okay, so next time then we'll do curvilinear coordinate systems. Nice. You? Thank you, Dr. Shu.
That last line.